There is a query about one of my lectures by email. A person by name Renzi Matthew. Is that person here? The person Renzi Matthew has sent me a mail that is Renzi Matthew here. Renzi Matthew.
No, sir. He is not there.
Anyway, she sent me a mail. I told you guys that whenever you send me a mail, I will only answer in the next class because that saves me a lot of writing in the mail. Plus, this question may be for others also, so they give the answer online. All of you can listen. So, unfortunately, Renzi is not here, but she can see it from my lecture, which will be uploaded in the website anyway. She had asked a question when we are talking about this 7-segment display. Last thing we did in the last class was 7-segment display, where you have segments A, B, C, D, E, F, G. How to get numbers 0 to 9 using this by appropriately enabling the corresponding segments. I had prepared a truth table from 0 to 15, 0, 0, 0, 0 to 1, 1, 1, 1. I said since we are going to use only 0 to 9, the combinations of the truth table corresponding to 10, 11, 12, 13, 14, 15, the last 6 have no use. So I used the don't cares there. In the truth table I used don't cares conditions, so that when I draw this Karnaugh map and simplify it, this don't cares can be taken wherever necessary to simplify my map. The question was, why do I do that? The same reason I have already said I've already hello. Hey, something is. So I already said the use of don't care is, if we want it, it can be taken as a 1 if that can reduce your simplification. We can reduce the hardware. If it does not, you do not have to take it as a 1. A don't care can be treated as a 0 or a 1. If you consider it as a 1, sometimes the map gets simplified. That is the use of don't cares. And when do we put don't care? The corresponding input condition will not occur. In the case of this question, 7-segment display, we are going to display only numbers 0 to 9. Number 11, 12, 13, 14, 15 are not going to come. When you are sure we are not going to have more than 9 for one digit, of course. If you want a second digit, you put a second 7-segment display. You can have any number of digits, as you can see in the clock or the bank teller. But for each of these digits, we have only from 0 to 9. When I want only 0 to 9, what is the point of using the combinations 10, 11, 12, 13, 14, 15? So the input combination, because the truth table will have 16 combinations 0, 0, 0, 0 to 1, 1, 1, 1, because we are using 4-bit binary. So the last 6 combinations starting from 1, 0, 1, 1, 0 to 1, 1, 1, 1 do not occur. If it does not occur, then you can use it as a 0 or a 1, because it is not going to occur. And I put a don't care, and when I draw my Karnaugh map using 16 cells, 4 input Karnaugh map, these don't cares will help us to simplify it, because the logic gets simplified if you have more don't cares in the map. That was the logic. I think I explained it earlier also when I introduced don't cares to you. Again last week when we discussed this 7-segment display, I made it clear, but it is all right to have question even if I made it clear. If you think it is not clear, you can always ask me questions. So good that this question came, I have now clarified it. Unfortunately, the person who has raised the question is not here. She is from, I think it's a she, Renzi Matthew, LBS College, Kasargod, Kerala. I hope that person will see my course which is going to be uploaded in the website and then get the clarification. I will also send her a mail saying that I have explained this in today's lecture, please go and see that. Any other questions do you have from last week or before? Any questions? No questions. We will start with a new topic today. Of course, this is a continuation of the implementation of first SSI, now MSI, using gates. What are the various applications we are going to have? Adder, because you see, one of the major components of any digital system is an arithmetic unit. You take computers, you need arithmetic unit. You take calculators, you need arithmetic unit. Microprocessors, you need arithmetic unit. ALU they call it, arithmetic and logic unit. So, one of the basic operations which most of the digital circuits or systems are expected to perform is addition. So today we will start with an adder and we will also see how we can make a subtractor. Adders and just adder subtractor. See, we have binary digits, bits. So numbers can only be 0 or 1. It's very simple to add 0 and 0, 0 to 1 or 1 to 0, 1 to 1. So if you have two inputs, A and B, you want to add this. We have a sum. So we have AB sum. Well, yes. When both are 0, sum is 0. This is 0 and 1, the sum is 1. When both are 1, we are adding 1 to 1, it becomes 2. 2 is 1, 0 in binary. So I can only put a 0 here and this 1 has to be accommodated. So I have one more output called carry. That we do in a paper and pencil addition also we do that. You are adding 23 to 84 decimal, 3 plus 4 7, 2 plus 10, but I can only put a 0 here, the 1 gets carried. The same concept here. Now, this is a simple circuit. You have a truth table. As you can see, sum is the exclusive OR of A and B. And carry is A and B. This is my adder. Very simple circuit. One XOR, one AND. The problem is I am never going to add 2 bits. I am never going to add a 1 to 0 or 0 to 1. I can do it in my head. I don't need a computer, I don't need a hardware. I don't need a pencil and paper. So I need to add usually several bits. if you are an 8-bit representation, sign magnitude or 2's complement, we will have plus 120, minus 128 to plus 127, two such numbers to add. So, we need a multiple bit adder. So, when you have a multi-bit adder, this carry has to be fed into the next bit position. So, these two inputs A and B alone are not sufficient. We need an extra input called carry in. If I am adding bit after bit after bit after bit, the carry from one position has to be fed into the second position. That is what happens in our decimal system also. You have a carry from one position, it goes to the next position. Carry from that goes to the next position. So, carry has to be propagated. So, I need another input called carry in. So, this is my A, B and C in. I have outputs sum, carry out. This adder which does not take into account input carry is called a half adder. This adder which takes into account the input carry is called a full adder. In full adder, I have 3 inputs and 2 outputs, so my truth table will have 8 rows. This is my truth table. Sum is 0, carry is 0, sum is 1, carry is 0, sum is 1, carry is 0, sum is 0, carry is 1. First 4. Now it's sum is 1, carry is 0, sum is 0, carry is 1, sum is 0, carry is 1, sum is 1, carry is 1. This is the truth table of a full adder. I can draw the Karnaugh map for this, simplify it, get the logic. All this is not necessary. Now you have become experts in Karnaugh maps, how to draw a Karnaugh map from a truth table and how to get a terms from the truth table, Karnaugh map, and then how to draw it using gates. Since we know all of that, I will not go through this exercise. I will simply give you the circuit. The circuit will have one exclusive OR whose inputs are A and B, and another exclusive OR whose input is sum of this, half adder sum. This is a half adder sum, A and B only gives you a half adder sum. But the carry has to be taken into account, so I need one more exclusive OR whose input is carry in. So the output is sum. So sum of the A, B and C n of a full adder is A exclusive or B exclusive or C, or 2 exclusive OR gates. And carry out is very simple equation. This is I can draw the K map for the carry out. This is 0, 0, 0, 1, 0, 1, 1, 1. This is A, C n, this is A, B, A, B, A, C n, and B, C. So that means I have 2 AND gates, 3 AND gates. AB, AB, AC in, BC in. Feed all these into an OR gate. This is carry out. So full adder has 2 exclusive ORs for sum, 2 input AND gates, 3 2 input AND gates, 1 3 input OR gate for the carry. These were only 1 bit. We never do a 1 bit addition. There is no point. Who wants to add 1 plus 1 plus 0 or whatever? You have multi bits. Usually today's computers, ALUs are very large, 16 bit, 32 bits, 64 bits, 128 bits. So several such full adders will be connected in series or cascade to get the final output. So a multi-bit adder will have several of these. I have one input where I feed, so let us say there are 4 inputs, 4 bit inputs, A3, A2, A1, A0, one number, B3, B2, B1, B0 second number, add them, you have S0, sum 0, sum 1, sum 2, sum 3, and there will be a carry overflow, so this will be carry out. And usually there is no carry in the first bit position. You can always use a carry in if you want, but it does not happen. Carry in is not there for the very first bit. So this is how it is going to be. A0, B0, A1, B1, A2, B2, A3, B3, C in, feeding to this C in, C out, C in, C out, C in, C out, going to C in. This is the final carry out if you want. This will be sum 0. Each of these is a full adder. FA stands for full adder. There are 4 full adders. Each having 1 bit of A and 1 bit of B as inputs and carry from the previous bit position as input. Output will be a sum and a carry out which goes as input to the next carry, as input carry to the next bit. Very first stage, C out, C in may not be there, it may be 0. But when you have multiple bits, 4 bits, 8 bits, 16 bits, 32 bits, you should always have this type of combination. C in should be provided in case it comes from somewhere, because it may have 4 bits and this 4 bits can feed into another 4 bits. So this C out of this 4 bits will go as C in with the next 4 bits. And each of them is this circuit. Each of these is a full adder circuit. We have this type of gates for sum, this type of gates for the carry. Such a circuit is called a ripple carry adder. Why is it called ripple carry? The carry from one bit position goes to the second bit position, from second bit it goes to the third bit, from third it goes to fourth. So the carry ripples through. Put a stone in a tank or a water tank or a water body, a ripple is generated and the ripple carries to the next, like that, waves. That's why it's called ripple. The ripple carry, the carry is like a ripple in a pond where you throw a stone. Now, this is the usual standard 4-bit adder circuit you will find in all books. 4 bits only they give because it's easy to draw. But nobody even uses 4 bits nowadays. 4 bits is only 0 to 15. Another 4 bits 0 to 15. So I don't think I need a big electronic hardware for this. But as I said, 4 bit is only an example. The same concept can be applied to, extended to 8 bits, 16 bits, 32 bits, 64 bits, 128 bits, whatever number of bits you have. This is for addition. As I said, the most, one of the...
నువ్వేదో నీకు కావస్తే చేసుకో నాకు కావస్తే కాదు వంకాయలు ఉన్నాయి వెళ్ళ తాగి వేయని కొడతా ఆగు దీంట్లో వాయిస్ వెళ్తుంది.
Anyway, now I said adder is one of the basic components because most of the hardware, electronics, digital hardware or digital systems, you have arithmetic logic unit, and one of the basic operations of arithmetic is adder. But then it's only adder alone will not do. Adder, ALU stands for arithmetic logic unit, and even arithmetic is not completed by full adder because arithmetic will have adder, subtractor, incrementer, decrementer, etc. So we will see how a subtractor looks like. Subtractor will have two inputs, x and y, and the sum, the difference between the two. D is, difference is x minus y, we will assume that, x minus y. Now, you have two inputs, x and y. D is the difference. So I have x, y, d. If both are 0, it is 0. 0, this is 1. I want to subtract 1 from 0. Like you have a decimal numbers. I want to subtract 17 from 23. I have to subtract 7 from 3, which is not possible. What do? I borrow 1 from here, make it 13, and then write the result as 6, and then this becomes 2 becomes 1 because I have already borrowed 1. So this becomes 1, so 1 minus 1 is 0. Same concept here. I have to borrow from this position, so I need one more input called B out, borrow out. In addition, like you had carry in, carry out, we have borrow out here. So 1, 1. When I borrow, this becomes 2. 2 minus 1 is 1 and the borrow is 1. 1, 0, no problem, because x is greater than y, no borrow. 1, 1 also no problem because this is 0, no borrow. Looks like the same as a full adder, half adder. So adder or subtractor, the D is x exclusive or y. But borrow is x bar y. B out. So difference is x exclusive or y. Borrow out is x bar and y. X bar and y. In the adder we had different sum is x and y, x exclusive or y. Carry was x and y. Here it is x bar and y. That is the only difference. Again the same concept applies. I don't want to do a single bit subtraction, I have multi-bit subtraction. That means I should have a place to put the borrow out from the previous position. So we have multi-bit addition, full subtractor we have. The full subtractor we have. So this is half subtractor. X, Y, B in, borrow in, D borrow out. Now this will be, difference will be 0, now I am subtracting x minus y, remember that. So, but we have a borrow also, so we will have a 1 as a difference and borrow 1. Then we will have the same thing here, x is 0, this is 1, I have a 1 and a 0, 1 and a 1. Then I will have 1 and 0. Oh, I am sorry, I will put it the other way. D I will first write 0, 1, 1, 0, 1, 0, 0, 1, same as a full adder. B out would be 0, 1 1 1 0 0 0 1. So, same logic again. So, if x is 1 and y is 0, you have output 1, no borrow. If x is 0 and output this is 1, because borrow is already 1, so you already borrowed in input borrow is there, so it becomes 0, but then borrow out is there. Here of course both are 1, I have already borrowed 1, so it becomes 1 and a 1. Circuit is same for this, like full adder. X, Y behind DI, D difference. Output will be, borrow out is slightly different. This is the same as a full adder carry table, except that this reverse. So, now this is the borrow out would be x bar di bn, x bar bn x bar y YBI. Again the same 3 gates feeding into NOR gate. B out, this is x bar, B in, x bar, y, y, B in. Same logic as, difference is same logic as sum in the full adder. Carry, borrow is the same logic as the carry out of the full adder, except 2 bits have to be inverted. Actually it is only 1, x bar has been inverted, 1 extra inverter. This is a full subtractor, but generally we do not do subtraction like this, we know that we already talked about it. When we talked about number complements, complements of numbers, 1's complement, 2's complement, we said subtraction is carried out as addition of complement numbers. You take 1's complement or 2's complement. If you are asked to subtract x y from x, you take the complement, 1's complement or 2's complement of y and add that to x. That is easier way to do it. Because this is again the reason, see, this is, to write this table is a little cumbersome. You have to imagine borrow out, borrow in and all that. More than that, this one logic for adder, another logic for subtractor increases the hardware. Suppose I have a 8-bit or 16-bit adder subtractor, I have a 16-bit full adder and 16-bit full subtractor is too much hardware. So, if I can use the same 16-bit full adder to subtract also, then it will be nice. Also it saves my botheration of writing the truth table for subtractor. So, we will see, we have already seen this, I did not draw the logic at that time. I explained to you what is 2's complement system, what is 1's complement number system, and I also told you how it can be used for subtracting one number from another number by simply adding. We will do this in hardware now, that is we have to draw the circuit diagram. Very simple. Suppose I have a full bit, 1 bit full adder. Oh, by the way, this is all half subtractor, this is called full subtractor. X, Y, B in, D, B out.
पिछला चल रहा है क्या वही
X and Y as inputs and B out. So for a single bit, using 2's complement or 1's complement number, I take a 1 bit full adder, I feed A and number or X, you want to call it X is fine, and Y I invert it. What is a 2's complement, 1's complement number system? Inversion of each bit. But subtraction is only addition of 2's complement, not 1's complement. Addition of 2's complement of Y. So we need to use the carry in of the full adder and connect a 1 to this. 1 is logic high. It can be 5 volts in your system, it can be 3.3 volts in your system, it can be 1.2 volts. Whatever is your logic high, that voltage has to be applied to carry in. Then we will have what you call a sum as a D and what you call as carry as B out. Is this not very simple? Instead of doing 2 sets of logic, writing the truth table, etc., all you have to do is to invert this Y bit for subtraction. But then again we don't do 1 bit. Nobody does a 1 bit subtractor using a 1 bit adder. So multi-bit. So let us look at a 4 bit full adder which can be used as a subtractor also. So multi-bit adder subtractor. So we will do a 4 bit adder subtractor. I will take a 4-bit full adder. That means I need 4 full adders in series. Four full adders. To this I feed A's and B's. A0, see the numbers to be added are or subtracted. A0, A1, A2, A3. The other way, I am sorry. A3 is MSB. B3, B2, B1, B0. This is A0, B0. But we can't feed directly B0 because we don't know whether we are going to add or subtract. With subtraction, I like to have B3 inverted. If it's adding, I mean B0. If it's adding, I want A0 and B0. Subtraction, I want A0 and B0 inverted. Similarly, A1 and B1 if it's adding, A1 and B1 inverted for subtraction. So what do? So I have two combinations, two possibilities. Either B has to be fed as it is for addition, or B has been inverted and applied for subtraction. So how am I going to do that? I am going to use a simple exclusive OR gate. I will tell you how it is. I have an exclusive OR gate here. I feed my B0 into the exclusive OR gate and connect the output to this. The property of the exclusive OR gate is to either put B0 directly into this or invert it and put it to that. We will see how to do it in a minute. Before that I will complete this. A1, B1, so I have connected A is directly to the full adders, B is through an exclusive OR gate which will act as an inverter if it is subtraction, and it will simply pass it without inversion if it is addition. So I want two functions from exclusive OR gate, pass it directly or invert and pass it. So I need to, I only use one input of the exclusive OR gate. The other input of the exclusive OR gate, I will connect them together. I will connect them together. I will put a S here. S is 1 for subtraction, zero for addition. Now I will explain what happens. A0, A1, A2, A3 go directly into the full adders. B goes B0, B1, B2, B3 go to the full adder with one input of the exclusive OR connected to that and second input of the exclusive OR connected to S, a signal. That S is an input which is 1 for subtraction and 0 for addition. So if it is 0, whatever appears here will go directly. What is the exclusive OR truth table? X, Y, F. So if it is F is, the second input is 0, when one of the inputs is 0, the output is same as the other input. In exclusive OR, there are two inputs. One of the inputs is 0, the other input output is same as the other input. If one of the inputs is 1, the output is inverse of the second input. So if X is 1, output is 1 if Y is 0, output is 0 if Y is 1. If X is 0, output is 0 if Y is 0, output is 1 if Y is 1. So by making S is equal to subtraction signal, if it's a subtraction, I will get B0 inverted, B1 inverted, B2 inverted, B3 inverted. If it is addition, B0, B1, B2, B3 go through without any change. So now I have a full adder whose inputs are A's and B's. If it's an addition, A's and B's remain intact. Subtraction, A's remain intact, B's get inverted. That's all we wanted. One's complement is inversion of each bit. But we need 2's complement. 2's complement, we know that is 1's complement. We have done this in the earlier exercise. I have also given an exercise in assignment 1. We have talked at length about 1's complement, 2's complement, how to make 2's complement, 1's complement, all that. 2's complement is, 1's complement is inversion of each bit. 2's complement is inversion of each bit plus 1, that is 1's complement plus 1. So where is the plus 1 going to come from? That is going to come from C in. The first input normally does not have any carry in the very first stage. I said that. Very first stage there is no carry input to the full adder. Now I can make it 1. Yes. Or in other words, the same yes I can feed here. If it is addition, this is 0, this is also 0. Subtraction, this 1, this also 1. That is all there is. And then this carry goes into the next stage. And carry out. This is S0 or D0 difference, S1 or D1, S2 sum 2 or difference 2. I don't have to write like this, slash. This is S0, S1, S2, S3 of a full adder. First bit sum, second bit sum, third bit sum, fourth bit sum. Automatically this becomes difference 0, difference 1. So this extra slash is not required. It is actually S0, S1, S2, S3 of the full adder also acts as D0, D1, D2, D3 of a full subtractor. and that will happen only if Cin is 1, which is happen when S is 1. In this case, all these B's are going to be inverted. Now you can always take carry out or borrow out. Only thing is, if you have overflow, you will have to detect it by, we know how to detect overflow. I told you last time when we talked about overflow in addition. You have to put these two into an exclusive OR gate. This is overflow. If overflow occurs, these two bits will have different values. If this carry and this carry are the same value, there is no overflow. If this carry and this carry are different, then there is overflow. Of course, don't have to worry about it. We are only talking about 4 bits now. This is called adder subtractor. I use 4 bits. Again, you can use it 8 bits, 16 bits, 32 bits, 48 bits, 64 bits, whatever number of bits you want. So now we have seen, first of all, we said that arithmetic unit is very important part of any digital system. We first saw half adders, and we decided that one input is extra required because of the carry in from the previous position. So we saw full adder, and we drew circuits for half adder and full adder. Then we went to subtractor, half subtractor without borrow in, or full subtractor with borrow in and borrow out, and we drew truth tables for that and drew the circuits. But I said subtraction has no meaning, because in digital logic, digital hardware, a full adder or adder is going to double as subtractor. And I told you how to do that earlier in my lecture theoretically, that subtraction is nothing but 2's complement addition. I drew a 1-bit adder subtractor where 1 bit was directly given, other bit was inverted and given, and carry in was given. That is a 1-bit subtractor converted, 1-bit adder converted into a subtractor. Then this is a multi-bit circuit. If I am sure I am going to only do inversion, if I am sure I am going to do only subtraction, not addition, I don't need all these exclusive OR gates. I simply invert it, invert it, invert it, invert it, and put as Cn 1. If Cn is 1 and all these bits are inverted, it becomes 2's complement. Then I get difference, 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 difference. But I don't know when it's going to add or subtract. Same hardware will be used. You will give a command for add or a command for subtract, in which case you need a signal called S. S tells you whether this S tells the hardware whether you are going to add or subtract. S is 0, it's addition. S is 1, it's subtraction. S is 0, nothing happens, it's as if it's a full adder. S is 1, the carry in is fed to add 1 to 1's complement. This 1 is required to add to 1's complement because only then becomes 2's complement, and each of these bits is inverted. So you have sum or difference depending on which adder subtractor. Of course, the carry out, which also is borrow out. Of course, overflow is a condition where this carry and this carry are the same signs, different signs, then it's called overflow. Are there any questions? Ramesh, can you unmute for a minute, and then if there are any questions, I will take.
Yes, sir.
So
Yes,
Ramesh,
sir. Yes, sir.
you can unmute for a minute. If there are any questions, please. What? Little noise I get. Any questions? No questions. Okay, please mute them again, sir.
Okay, sir.
Nobody seems to have anything to say. Somebody has a question? Raise your hand. Sir.
Yeah. I will unmute.
Who is that?
Yeah, please ask a question.
Who is this person? Raise your hand first. Yeah, sit down. You can sit down and ask. What's your question?
Sir, I'm from Srimati. I'm Srimati from Karnaugh College of Engineering.
Very good,
Sir,
Srimati.
can you please?
Yeah.
Sir, can you please tell me? Can you please tell me the advantages of 4-bit adders?
There is nothing like advantage of 4-bit or 8-bit. You see, 1 bit only 0 and 1. We are used to decimal numbers. 0 and 1. Add them, both are 1, the added result is 2. Do you want an adder for that? 1 plus 1 is 2? No. So, we have to do multiple bits. Because in real computers or microprocessors or calculators or whichever other circuit uses adders, we will have several bits for A and several bits for B. There is no advantage of 4 is a very small number. Really today's computers or calculators or microprocessors will use 16 bits, 32 bits, 64 bits like that. But I don't think I can draw a 64-bit full adder subtractor. It will take 2 classes to complete the drawing. And then the concept is clear. 4 bits means you can extend it to 8 bits. And also hardware wise it is available. 4-bit adder is available in the shop. Maybe 8-bit adders, I don't know. But you can't buy 32-bit adder in a single, unless you design it in a FPGA or a VLSI. It's not available. You cannot go to the electronics parts store. We call it Ritchie Street here in Madras. You don't go there and say, give me a 64-bit adder. That fellow will not have it. So 4-bit is not an advantage. 4-bit is only a simpler way of telling you more than 1 bit is needed. When you have more than 1 bit is involved, how do you take care of it? So it's a simple example. All examples in the class have to be simple so that it can be explained in detail in the class. Drawings are easier so that you will also get the concept across. So otherwise there is nothing like an advantage of 4-bit adder. Is it clear, Arunai? Is that clear? Is that okay? Okay? Okay. Done. Anybody else? Yes, sir. Somebody else is there. Arunai.
Yes, sir.
Hello,
No.
sir.
You here.
Sir.
One person at
Hello?
Yeah.
Me, sir.
Sir, derive the expression.
Tell me
No.
one more
Sir.
time. I don't
Sir,
understand
for
you.
full,
Huh?
sir, for full adder, derive the implementation for the sum expression, sir.
Derive it. Huh?
Implementation for the sum expression.
I understand your question. Why should I do it? Why don't you do it? It's in the book. You look
Sure,
at my
sir.
NPTEL lecture. It's a very simple circuit, I say. So 3 bits and all those things. Don't look upon this as a 4-bit adder.
4-bit adder.
Don't look upon this as a 4-bit adder. Look upon this as a multi-bit adder. 4 is an example for me to do it in the class simply. So there is nothing like a 4-bit adder advantage or 8-bit adder advantage. Multiple bits are required to be added today. You nicely feed in the numbers in your calculator. You have a calculator, you keep on punching numbers in decimal system. It has to be converted into binary and it has to be added. Who will do the job? The hardware inside. What that hardware is going to look like, that is what I am describing to you. So application is addition. You can't ask me what is the application of addition. You want to add your monthly expenses, you need an adder. You want to add your marks to find out your average, you need an adder. What is the advantage of adder? There is no answer for that question. Everything is an advantage. Yes. Somebody else has a question here, sir, in the corner. 2 more persons, please, quickly. Yes.
Sir, I'm having a question. Sir, can we design digital circuits where number of bits will be separate from 2 power n? That means I have seen an Arduino board where it was having around 20 pins. So I was confused that whether we can design it or we can only have we can have 4 bits, 16 bits, 32 bits circuits.
See, it is a question of component buying. If you are going to buy a component in the electronics parts store,
Yes, sir.
if you want 17-bit adder, they may not have it.
Yes, sir. That's the same question.
No,
I
let
wanted
me
to ask.
complete the answer. I got your question.
Yes, sir.
You can buy a 16-bit adder, but you can always design a 17-bit adder by using a 16-bit adder, 1-bit full adder, and do it yourself. Nobody prevents you from using anything other than what is available in the market, right? Something like buying a shirt,
Sir.
ready-made, or somebody tailors it for you.
Sir. My question is related, sir. We can have logics made of 0 and 1. So we can have only those logics which fit the relation 2 power n. So, no, sir.
Not necessary.
Not necessary.
16-bit you don't have to design again, it is there. You go
Yes,
to
sir, it's
market
there.
and buy 16-bit adder.
Yes,
You
sir.
don't derive a logic, you don't write the truth table.
Yes, sir.
And then you say, if that is the sum is this, 0, second bit is 0, what is the output? Sum is 1,
Sir.
like that. That is all.
Sir, as you said, we can have 17 bits. For that, we have to add one separate adder.
Yeah.
So when we will supplying signals to that 17-bit adder, so the codes which we will be forming from 0 and 1. So, sir, how the 17th code will come out?
17th bit also you have 0 and 1. Everything is only 0 and 1. See, 16 bits, how are you going to feed the inputs? 16 bits are going to feed 16 zeros and 16 ones. 16 A's and 16 B's.
Yes, sir.
Now you have a 17th A and 17th B which you feed to the 17th full adder. I don't think there is any complication there. But generally today's electronics market is so cheap, they will buy a 32-bit adder and use it as an 18-bit adder or 20-bit adder instead of doing this extra effort of designing. Do you listen me? Are you hearing me,
Yes, sir. Yes, sir. I'm listening.
Today it is so cheap. Those days they were counting number of gates, it's expensive. Boss will say, why are you using 18-bit when you can only 17 bits will do? Today the effort,
Raju,
how much time you are going to spend on this is more important than the cost of this.
Raju,
Commercial, yes, sir.
Something like your
take online class.
something like the earlier we were worried about 2 rupees.
Yes,
When
sir.
I was a student, my father used to give me very little allowance. Today your fathers give you credit cards. They don't care about money. That is what it is today. How many credit cards do you have? 5? Okay, any question there? Any more question? So don't do counting of the gates. Those days are gone.
Yes, sir.
Counting of the gates is gone. Today I want to save the effort. amount of time you want to pay another engineer, you don't want to pay another engineer. That is the point. Engineers are more expensive than the hardware today. You are going to be paid 100,000. What is that? Nowadays they start with this 5 lakhs to 10 lakhs. That is cheaper. That is more expensive than buying a full adder, another full adder for 100 rupees in Ritchie Street. Okay, Ritchie Street is a local electronics market. Okay, tell me, somebody else, Aruna is also waving. Please.
So can we implement with the enable input, sir,
Any other?
for full adder?
What?
In
Say,
4-bit,
say it one more time clearly.
in 4-bit adder, can we implement with the enable input, sir?
Any other input? Huh?
Enable inputs.
Enable input is no. Normally full adders don't come with an enable. You can also introduce an enable by putting an extra circuit outside. Enable input is not generally done. For full adder, there is no enable. If you go and buy a full adder in the market, 4-bit full adder, there will be 4 inputs for A and 4 inputs for B, 4 sum and 1 carry output, 1 carry input, and power supplies. A 4-bit full adder in the market will have, if you buy this as a IC, 4 A's, 4 B's, 1 C in, 1 C out, 4 sums, and 1 power supply, and 1 ground. That's all they will give you. There is no enable input in this. But if you want to enable it, you have to make one of them, A will come only when you enable it, B will come only. So you have to put an extra outside circuit. Extra circuit including some AND gate, for example. You put an AND gate and then pass your A through that and enable the AND gate with the other input, then enable is possible. Normally not done. Theoretically possible, practically not done. It's not available that way in the market. Okay? Let us move on. Can we? Yes. Please mute them, sir.
Okay, sir. Okay, sir.
Thank you. Is this Karnaugh or Ramesh? Oh.
This is Ramesh, sir.
Yeah, because Kannan's voice also, you talk like Kannan.
Okay, okay.
Your voice and functions, everything. You are now become Kannan.
Thank you, sir.
Okay, now, today I want to do one more thing. BCD adder. See, normally in a calculator, that girl was asking, what is the application? I need to add. I have bought a calculator. I want to add. Nowadays, the kids, nowadays not kids, I mean you college students, don't know how to add. Use a calculator for everything. Supposing somebody comes and asks you what is 17 plus 17, you will say put a calculator. I know. So you want to feed in 17, another 17, yes sir, it is 34, yes. You are right, I will say. But then I need 17 and 17 as inputs, not 17 in binary form. This is called decimal input. We already called it what? BCD. Do you remember? I used the term BCD. BCD stands for binary coded decimal. A binary coded decimal input BCD stands for binary coded decimal. We have 0 to 9, and then next is not, this is 0, 0, 0, 0, 0. 9 is 1, 0, 0, 1. After 9, you have A, B, C, D, E, F in a hexadecimal. Here we have after 9, 10. For 10 I need 2 digits. It will be 0, 1. So this will be 1 0. 11 will be 1 1, etc. up to 19. So when I add BCD numbers, I have to handle 0 to 9. Number exceeds 9, I should use another digit to represent it is more than 9. So that will be 1 again. So 1 0, 1 1, 1 2, 1 3, etc. So I am given a 4-bit adder. If you go and buy a market, or even if you design your own circuit, you are doing a 4-bit full adder. Numbers are binary. A and B are binary numbers. They can take from 0 0 0 0 to 1 1 1 1. But now I want to convert this into a BCD adder. So how to convert a binary adder into a BCD adder? So the binary numbers are B3, B2, B1, B0, binary, goes from 0 0 0 0 to this is 0 to 9. Already said that. Now next digit I want 10, 11, 12 up to 19. Second digit. So there will be 2 binary adders. One binary adder for 0 to 9, another binary adder for second position. Now when the sum exceeds 1001, what I do is I add a hardware, extra hardware to get this. So for example, there is no carry up to 15, let us say 15. So 15 is 1 1 1 1. You try to exceed 15, you will have a carry, again it starts 0 0 0 0. And finally it will end up with whatever 1 0 0 0 1 0 0 1. This will be 16, this will be 17, etc. Up to 19 we want. Now I have to convert this after 9. When 10 comes, I want to have it as 16, because if I add 1 0 1 0 is a binary 10. But I want this to be represented as decimal 10. Decimal 10, 10. This is 10 binary. So what do? I want to make it as a first position 0, second position 1. This 1 corresponds to this 1, and this 4 bits corresponds to 0. You can look at this number carefully. 1 0 1 0 becomes 0 0 0 0 with a 1. So in other words, binary 10 has become binary 16. 1 0 0 0 is binary 16. 15 is 1 1 1 1. 16 is 1000. So adding 6 to this, if I add 6 to this, what happens? If the number exceeds 9, the number is 10 and above, we will add a 6 to it. So I should detect this number. Up to 9 I am very happy. Result is 0 through 9. Whether it is a BCD number or binary number, there is no difference. BCD number goes from 0 to 9 and then again 0 to 9, again 0 to 9. Binary number from 0 to 15 and then 0 to 15 and 0 to 15. So when the number is 10, 11, 12, 13, 14, 15, that is after 9, whenever the number exceeds 9, that is if the number is 10, 11, 12, 13, 14, 15, if I add 6 to it, I can make it a decimal number with 2 digits. Now the next number will be 1011, 11, add 6 to it, this is 17, 1, this is 1, so this is 1010, so this will be 16, this becomes 17. Now we have to have an adder circuit, first 4-bit adder, then I should have another adder circuit in which I will add the result of 4-bit adder with a 6 number and then I get my BCD adder, but I can't do it all the time, I can only do it when the number exceeds 9. So it requires a special logic. I wanted to talk about it today, but now it's time. I would like you to read up, I will do it in next class. On Wednesday I will again start with this, we will go through it. But I would like you to do 2 things before that. It is available in the book. Go to BCD adder, either in any textbook you are using, Mano or Tossi or Roth or any other Weckerly, any book you are comfortable with, or go to Google, or go to my NPTEL lecture on this. I have an NPTEL lecture on BCD adder. If you do that, it will be a great help for me on Wednesday, because today I want to finish this also. So we are now lagging behind. That is all right. I have no problem, because my job is not to finish material. My job is to make you understand material. So I don't mind going slow if that is needed. All these questions you asked, I am very happy, because you have questions you ask and then it becomes clear. And when you ask a question, you are also helping your friends, because somebody may have a question but he or she may not ask. So if you ask the same question, the other person will get benefited. So I am not telling you not to ask questions, please continue to ask questions, but sometimes I will ask you to read up and come. When you read up and come, it helps a great deal for me. So before you come on Wednesday's class, go to any textbook and read BCD adder. How a binary adder converted to BCD adder? Very simple. You have to add 6. If you are adding to the sum already in a full bit adder, 4-bit full adder, sum is already there. To that sum you have to add 6, means I need one more full adder, 4-bit adder. That is number 1. Number 2, you don't want to do it always, only when the number exceeds 9. So these 2 conditions you have to do, that's all. You have to detect the condition when the number exceeds 9 and add 6 to the adder. That's all there is. Read it up, watch my NPTEL video, or Google it, or talk to a friend, or talk to a teacher, whatever is there. So if you come with a little bit preparation, I can quickly finish it off and move on next time. Any questions? Sir, Ramesh, please unmute them.
Sir.
Last,
Yes, sir.
any remarks? I am going to close down now in another 1 minute or so. Please tell me if you have any questions, sir. Comments? Are you going to do this reading up I am asking you? Yes or no?
Yes, sir.
Oh, please. Good.
Yes.
Yes, yes, yes. If there are no more questions, I will stop now. If there are questions, you raise your hand. I will wait for another 30 seconds. Okay, we'll see you on Wednesday.